Okay, so Unit 3, here's kind of an overview because it's a miniature unit. Meaning it's going to be over before you know it, but that's also nice because it's not a lot. As you can see, there's only 3 I cans. Okay? In this unit, what we are learning is we are learning about the 3 different types of bonds in chemistry. Maybe you've been introduced them into other ones. They're known as ionic, covalent, and metallic. The 3 I cans are based on understanding these 3 types of bonds from all 3 sides of our chemistry triangle. Meaning, today we are going to be focused on the symbolic side, meaning, can you identify if something is ionic, covalent, and metallic if I write a symbol, such as NaCl? By the end of class today, you should be able to say, oh, that's ionic because of this, okay? Second thing that we're going to be covering today is the molecular side, meaning what does it look like, right? If we could magic school bus into a molecule, right, what is the difference between ionic, covalent, and metallic? Okay, then next time and the time after that, we'll be focusing on the what do you see side, meaning we're going to go into the lab and do an actual real chemistry lab. Yay! Hallelujah, finally time. Where the goal is I'm going to give you a random substance, and by performing various tests on it, you should be able to identify, oh, this substance is ionic, covalent, and metallic. So that's kind of the way the 3 I cans are separated is what does it look like from our eyes? How does it behave? What does it look like at the molecular level? And then how do we write it symbolically? The test for this unit, just to kind of give you a heads up, is a combination test where half of the test is on Mastery Connect like you're familiar with. The other half of the test is actually a lab practicum, meaning on the day of the test, I'm going to give you 3 unknown substances, and part of the test is you have to go into the lab and figure out if they are ionic, covalent, and metallic. So kind of keep that in mind as we get into the lab, that we want to get really good at those skills because you're going to have to do it independently eventually. Okay, we have 3 days and then we're testing on this unit. So today we're learning those 2 things. Next time we're learning all the different ways you can test it in the lab. The time after that will be like a practice run of unknowns. So pretty much kind of like what the test is, but you'll get to work with the lab group, ask all the questions you want. And then that 4th day, you'll do it by yourself. Okay? All right, so let's go ahead and jump right into it. Okay, so first off, let's talk about in general why things bond. Okay? A chemical bond is an attractive force between particles, atoms or ions, that bind them together. Now, you need to understand that chemical bonds there's varying strengths, but it is a very strong force. Yeah?
I think we can move the trophy.
For sure. Is that like right in your viewpoint? Yeah. Okay? The reason why atoms bond is because it's all about stability. Okay, by bonding with other atoms, it causes them to become stable. That's why some atoms don't really bond at all, is because they're already in a position of stability. Now, what makes something stable is this idea of having a full valence shell, which typically brings up this idea of the number 8. Now, it's known as the octet rule, oct for 8, because it's all about wanting to get 8 valence electrons. You need to understand, though, that it's really more of like the octet guideline. It's not actually always 8. I'll be honest, in general chemistry, it normally is. But if you go and study higher levels of chemistry, you'll learn that no, atoms can actually have like 10 electrons or 12 electrons, and they are stable. But for now, it's generally 8. Okay? That's why we call this last family right here the noble gases. They're considered noble because they don't interact with the common folk because they're already stable. Some of them do form bonds, once again, because of that idea you can't go above 8. But the ones at the top, helium and neon, don't bond with anything in the entire world. Is anyone in here familiar with welding? Does anybody do welding?
Isn't that when you make pots?
No.
No.
I don't know what that called.
It's like fusing metal.
Yeah, that's like with a flame, like fusing two metals together with a blowtorch and
Would
stuff.
try
Right?
though. Have the effort of that.
But anyways, with welding, a lot of times I've just learned this because my dad's really gotten into welding. But when people weld, everyone actually kind of cool connection. They will use a noble gas. So argon's like a popular one, but they'll spray the argon gas as they're welding to prevent anything from bonding with the metal they don't want to bond. Because argon won't bond with it. It's also why, like, when they transport things that are really, really reactive, they'll sometimes surround them with helium. We actually are kind of running out of helium on the Earth. I don't know if you're aware of this or not. And it's not because of birthday balloons. It's because they use helium all the time as a protective thing when something is really, really reactive. They surround it with helium gas. So. Just a reminder of some vocabulary words we have talked about before, right? So anions are the negative ones, and cations are the positive ones. So that's one of the ways they can kind of form. Okay, so the different ways that they can achieve this octet is by gaining. They can achieve an octet by losing, or they can achieve an octet by sharing. Now, we've mentioned this before, but it's been a while. Can someone remind us why or how does something get 8 electrons by losing electrons? Remember? Yeah, Jeremy.
Isn't it just the fact that, like, say you have 2 on the valence shell, if you, like, lose 2, then that kind of shell kind of just disappears, and now the new valence electrons are the shell below.
Perfect. Yeah, it's that whole idea. I have a smiley face for that. I'll pass back those, by the way, and turn them in. If you give away all of your valence, this shell in a sense disappears, and the ones underneath are always full, right? Because atoms are like onions, and if you peel off one layer, there's a full layer underneath, right? And that's the whole idea. It's really not about having 8. It's about being full. So. Okay, first type of bond is known as an ionic bond. An ionic bond is formed through the transfer of one or more of an electron to another atom. So here's kind of a visual of molecular level, right? So this is like magic school bus, what we would see when 2 things ionically bond. Okay? Sodium here has 1 valence electron. Chlorine here has 7. So sodium says, hey, chlorine, take my electron. Because by getting rid of this one, like Jeremy said, it removes its outer shell, so it's full. This one now is full, so they're both happy. And then what holds them together is literally the positive and negative force that they turn into. Because by losing an electron, you become positively charged. By gaining an electron, you become negatively charged. And so they're like little magnets. Now, it's important to recognize that chemical bonds are not magnets, but you can relate it like a magnet. That's what holds it together. Okay, so that is your ionic bond. Once again, hence the name is because it's about ions, positive and negative things. Okay, all about that idea of the opposites attract, right? And so the cation and the anion are formed, and then they're bonded together through that attraction. Now, the way that ionics always form is it happens between a metal to a non-metal. So this is why we reviewed the metals and the non-metals on our warm-up. Can someone, by raise a hand, just remind us? I think we all got it from what I looked at the quiz, but can someone remind us where the metals and where the non-metals?
The non-metals are to the left of that little staircase, right? And then the non-metals are to the right, and the metals are to the left.
Perfect. So these are all metals except for
Hydrogen.
hydrogen, and then yeah, these are all nonmetals. The ones in the middle are called metalloids, and we'll kind of deal with those later. Okay? But that is, I'm just going to say. So the metal always becomes the cation, because they're always losing. And the non-metal becomes an anion, being the negative one, and then the opposites attract. Okay, so the ionic bond is the electrostatic attraction between the ions. Now, this is how you identify an ionic bond from the symbolic side. If I give you a formula, once again, such as, we'll just do ABr, potassium bromide is its name. The way you identify its ionic is by checking their location on the periodic table. You look and say, okay, where's potassium? Oh, potassium's a metal. Bromine is a non-metal. And so that's how you know it's going to be an ionic bond. So if a question just gives you a formula, that's what you're checking for. Okay? Now what's cool is if you think once again as these things are little magnets, right? Think of like a grain of salt, right? A grain of salt isn't like one Na and one Cl. It's like zillions of them. And what they do is all those little magnets line up into this really cool crystalline structure, where you have a bunch of positive, negative, positive, negative, positive, negative in 3D space. This is what an ionic substance looks like at the molecular level. Okay? It's this network of ionic bonds, and it's also often known as a crystal lattice. Kind of think like lattice is a ladder, right? Of like positive, negative beings all over. So, sorry, let me go back here. So, all ionic substances, we are called crystals, which is actually why all ionic things have a crystal-like look. Now, obviously, crystal is a little dependent upon how smashed up it is, right? Because even if you were to take salt and grind it really, really fine, it's probably going to look more like a powder than a crystal, right? Because you crushed it so small. But at bigger sizes, all ionic things typically actually look like salt. Sometimes just different colors. It's actually why all ionic substances are also called salts. The salt we eat is table salt, but anything that's ionic is actually also called a salt. That's why we call it like road salt, right? It's not the same thing you put on your food, but it's called a salt. Okay? And things like that. Yeah, don't put the road salt on your food. Okay? Now, what's important to recognize is the formula we write, so like for this, NaCl, this just tells you the ratio. It tells you for every one Na, there's going to be one Cl. But technically, in your sample, right, you could have like 20 of these and 20 of those. We don't really know, it depends on how much stuff you have. So the formula, that's what this means by empirically, is it's just the smallest ratio of how many each things you have. So that blank right there says the formula is always given empirically. And it's known as just a formula unit, because it's just a simplified ratio. Okay, so let's do just another example to have a visual here of what happens with an ionic bond. So we're going to do the equation of barium and sulfur. So the barium atom comes in contact with sulfur, what's going on there? So the first step is you've got to identify how many valence electrons it has. So this is also a review from last unit in terms of valence electron is we count these columns, skipping this middle section. Since barium is here, it has 2 valence electrons, so put 2 little dots on barium. Doesn't really matter, but just for vocab's sake, this is known as a Lewis dot structure, is where you just visually show the valence electrons. Okay, sulfur's in this column and has 6. So the whole idea is this one wants to give and this one's going to take, and it has to balance out. In this case, it's a perfect balance. We give 1 here and 1 there. Once again, because going to 0 makes the under shell full. This one has its outer shell full. So the reason why they stick is because by giving away 2 electrons, it becomes positively 2 charged. Sulfur is going to become negatively 2 charged because it's gained 2 more. And so now they link together. Okay? Questions on balancing out an ionic bond? Okay, so here's kind of the words of what we just did. Barium's going to lose 2 electrons. Sulfur's going to gain 2 electrons. And then the key point is that they're held together through their positive and negative forces. Now, we're not going to focus on a ton because next unit we'll do more balancing. It doesn't always work out in this perfect 1-to-1 ratio. Sometimes you might need 2 of one and 1 of another to make it balance out. But the big key is that they always have to balance. Okay, that's ionics. Any questions there so far? Yeah, Seth?
First blank of the top versus like ionic blank electrons will be
Transfer. Yep. Yeah, that's kind of like the main way we describe it is ionics all about transferring their electrons. So, any other questions on ionic? Okay, let's talk covalent bonding. Now, before we talk about, once again, it's important if you kind of like understand the meaning of words, then it tells you its definition. Can anyone think of other words in the English language that start with the prefix of co, C-O? Did you say copper?
Cooperation.
Oh, cooperation, yes. Other ones? Co-worker, good. Have a smiley face, by the way. Copper is one. It doesn't quite match the, but it does start with C-O. Other ones?
Coexist.
Coexist, good. Have a smiley face for that. Can anyone think of like a trend in all these words? Like accompanies another one? Yeah, there's this thing of like, or a couple, right? There's this idea of like togetherness. Okay, but a covalent bond is now about sharing their electrons. Okay, covalent is all about sharing, and here's kind of how it works. Okay, so like we said, chlorine has 7 valence electrons, right? Oh. Where's my other chlorine that was supposed to pop up here? Maybe it'll come up on this next slide. So hydrogen comes with 1 valence electron. Okay. Chlorine comes with 7. One way they can both be satisfied is by sharing and see how their orbitals overlap with each other. Hydrogen says, hey, I'll share 1 with you if you share 1 with me, and these 2 electrons now belong to both. So chlorine gets its 8, hydrogen gets its 2, because once again the first shell only needs 2 to be filled, and they're both satisfied. Okay? It's all about, once again, achieving that octet. Now, the difference here is with the covalent bond, is covalent bonds are formed between a non-metal and another non-metal. Because like Camille reminded us, our non-metals are the ones on the far side of the table. They already have a lot of electrons. So they're not really going to try to give away 7. So instead, they just find what ratio they need so they can both be satisfied. Now, once again, when we learn how to draw these things, we'll see sometimes they share 1. This is classified as a single bond. But they could also share up to 4, which is a double bond. And they could even share up to 6, which is called a triple bond. As of right now, scientists have not made a quadruple bond work. We'll kind of learn why that is later. But okay, so there's our shared valence electrons. Questions on covalence? Okay, last type of bond, metallic. Okay. Now this one by its name should be the easiest to identify symbolically. Okay, if ionic is a metal and a non-metal, covalent are 2 non-metals, metallic's going to be 2 metals, right? Hence the name. Now what happens is it's interesting because metals are all on the left side of our staircase. So there's a lot. So we have lots of options, but they don't have very many valence electrons. At most, they have 3. So if 2 things come in contact and they only have 3 and 3 each, there's no way like to get to 8 even if they share. So what happens is in a metallic bond, it's also a shared relationship, but it's like a community shared relationship. You can kind of think as metallic bonding is like communism. Woo! Everybody shares with everybody. Okay? So we often kind of call it a sea of electrons. All the metals release their electrons, and then the electrons just flow throughout the entire thing. So covalent is I share with you, you share with me. Metallic is everybody shares with everybody. Yeah?
That's why we use like metals and like stuff.
Yes, and that's perfect connection of when we go into the lab last time. Yeah, that's why metals are such good conductors, is because of those free-flowing electrons. See, so great connection. I have a smiley face for that. Questions on metallics? Do we have some more blanks to fill in?
I didn't get any of them.
Okay, so here's what happens. The electrons are released because they don't hold on to them very tightly anyways. Okay? Once you release your electrons, you become positively charged. So we get a bunch of cations surrounded by this electron sea. And then there's once again kind of this idea of a positive and negative force going on that holds it all together. One of the other chemistry teachers brought up this analogy that I thought was kind of clever for comparing our 3 types of bonds. Then I'll go to the next slide. Is imagine, you go ahead of it. Imagine I brought in a puppy, okay?
Oh no.
So an ionic bond would be I give Camille the puppy, but sorry, she's in the best seat, I guess. But then since she has the puppy, I'm going to hang out with her because she has the puppy. So ionic, held together, but I don't have the electrons, right? Covalent is we share the puppy with each other, so we both get a hold of it. And then metallic is we let the puppy run around the room.
Yes!
Everybody gets it.
And the puppy wants me.
I'm making it less the people at home can actually have a good show.
If it's ionic, I still get to see the puppy.
So what we're going to see here, everybody, is so once again, this sea of electrons, that's the magic school bus view of metallic bonding. What is so awesome with chemistry, if you connect it, is what is happening at the molecular level explains things that happen at our level. And that's kind of the big picture of going into the lab last time, is trying to make that connection. And a few things with metals are all because of this C. Number one, they're extremely malleable. Malleable by definition means it can be shaped without shattering. So clay, when it's wet, is very, very malleable. Clay, once dried, is not malleable. Okay, keep in mind we'll use a test of malleability next time where we pretty much hit things with a hammer. That's how you test for malleability. Ductility means you are able to draw it into a wire, which once again, metals can be pulled into a wire. Salt cannot be pulled into a wire. You can't make a wire of salt. It won't work. Okay? Luster is how shiny it is, and metals all have some sort of shine because that electron C. They are very good conductors of electricity, you brought up, and they're also very good at conducting heat because of this free-flowing electron C that they have. A few seconds to fill those blanks in. Everyone good there? Okay, let's do a little practice problem. I don't know if it got printed in your notes, so just go to that little space at the very bottom of the table, and let's do this for some smiley faces. Okay, so I want you to simply tell me, of these substances, is it ionic, covalent, or metallic? I'll give you 2 minutes. You can talk to your table buddy if you want. Ready, set, go. Smiley face for each. So what's that? 1, 2, 3, 4, 5, 6, 7. 7 smiley faces up for grabs. You could also go to the very last page. But you don't get any smiley faces if it's not written on your paper. You do it in your head. Sorry, I can't read them.
Yeah, it is ionic. That's the one where if the electron is transferred from metal to non-metal.
We got a metal.
That hydrogen's drinking.
Mike Fast. No.
Okay, let's try these out. So right now the first one, so NaCl. How do I know what to know?
No.
So it's non-metal is non-metal.
So it's not metal. Okay, let's do the next one. H2O. What is it? True. So how do I know what type of bond it is?
Yeah, sharing of electrons.
That's ionic. So that one, right?
Yeah, I think they share.
Good. So what am I looking at?
So that's all.
So look at the periodic table. Why is it coming in?
That's also.
Covalent are 2 numbers. That's right. H2O. Okay, next.
Sulfur.
Look, it's already there.
Non-metal
We also have.
I mean, it's metal.
We also have.
But it has two.
Hopefully the hardest part of these questions is just finding them on the table.
Yeah, we can find one again.
It's ionic.
Right? Because they're both metal.
I was gonna say maybe it's
It's also
what is the difference between covalent
Oh,
Is it? No,
it's non-metal and non-metal. And then the metallic.
Okay, when you're done,
Okay, yeah,
give me a pencil drop so I know you're finished.
So it's non-metal. So this one is covalent.
yeah.
And then C, metal.
Okay, wait, no, SOS is. Yeah, no, there's, it's.
What? Then it would be. What do you think?
Well, the red are
Yeah.
Oh, it's C.
Everything to the left of this case is on roll.
I would say that.
So this should
No,
most
it would be
metals.
metallic, because they're both metals.
Here's the thing, I don't know.
Oh, wait, is it all? No, they're all.
Okay, I'm gonna give you 20 seconds before we check it.
We got a. That's okay. I think that makes sense.
Five, four, three, two, one. Okay, switch papers with your neighbor and check theirs. Okay? And then just so I can kind of like get an overview of how we're doing, we're gonna use some sign language for you to show me your answer. Okay, so this is an I for ionic. This is a C for covalent. This is an M for metallic. Okay, I'd like you to hold it like under your chin, so like other people can't see. But you shouldn't be worried anyways because you're not showing me your answer, you're showing me your neighbor's answer. So, yep. Okay, NaCl, show me your answer, or the answer on your paper. I love how people are like, I can't remember what sign is. Just make something that looks like the letter you're trying to show. Very good, it is ionic. Good. Okay, H2O. Very good, covalent. This one's sneaky, why? Or which element is sneaky?
Hydrogen.
Hydrogen.
Because it's the only one that's not. on the-
Yes, it's a non-metal, but he hangs out on the metal side, right? So you gotta be careful with that one. Next one, TiO2 is ionic, titanium oxide. Okay, MgCl is ionic again, very good, magnesium chloride. ZnCu is metallic, very good. That's actually the chemical symbol for brass. So brass is a combination of zinc and copper blended together. NO, nitrogen monoxide, is covalent, very good. And copper 2 sulfate, ionic, very good. This one's kind of sneaky.
Got them all wrong,
So give yourself up to 7.
Oh, bro, you got the wrong zipper.
If you got it all right.
If you're not cheating, you're not.
I wasn't paying attention. So I didn't see her make it.
Oh, this is the wrong one. I just realized this is
It was so
Okay, any questions for ionic and metallic?
Explain number 7, like the 7th one.
Okay, give me your attention here. Last thing, everybody. This is actually a good one to go over. So this one, it's a little tricky, but if you go through just the process and identify, okay, copper is what?
A metal.
A metal. sulfur is a
Non-metal.
non-metal, oxygen is a,
Non-metal.
so anytime you have a blend of full, it's ionic. Even if you have multiple non-metals or multiple metals. Does that make sense? So, good question. Any other questions on this?
Okay.
Just left it on my desk. Okay, so your assignment tonight is going to have problems like this, and then also a few questions about the molecular view side. So I'll show you some pictures. You identify, oh, that's ionic, covalent, or metallic. Okay? Okay, so your assignment is on Canvas, so if you want to open up your computer.
Wait, are we not doing this little table?
So the table will be next time.
Okay, thank you.
Yep, yeah, good question. On Canvas, the assignment is called Identifying Chemical Bonds. I think it's like 18 questions, which they're pretty quick questions, so you should be able to get done, I think, before the bell rings, in my opinion.